So our last slideshow introduced us to the idea of rings. We've got here the A ring, B ring. You can see with a very small telescope. The A ring, the B ring, and with a decent telescope, decent amateur telescope, you see a C ring. Okay, not visible easily from Earth, except by the Hubble telescope, maybe, is this F ring, which is just outside the A ring. Now, the F ring was a very interesting sort of thing because as the Voyagers flew by, they sent back pictures showing the F ring sort of kinked and twisted a little bit. And that was a huge mystery right there as to what would do that. In fact, the whole rings were a mystery because dynamically all those particles going around in orbit there should gradually dissipate and spread out. So the rings should not be a stable feature. They should be something that dissipates. And so this was actually a big argument they had. Are the rings a long-term feature or are they a temporary feature? Did maybe a comet run into run into Saturn and break apart and make rings? They thought the Shoemaker-Levy 9 might make rings around Jupiter. In fact, there's one speculation that we might have two ringed planets after that. So there was all kinds of ideas here. Well, why do the rings even stay there? So that didn't seem to make any sense. Okay. But as they were studying this F ring, they noticed these two little moons. They're tiny little moons. In fact, we almost call them moonlets. Okay. Prometheus and Pandora. And they orbit right there inside and outside the F ring. And that really started the understanding as to how these rings work. The rings are not stable without having those moons. And we call them shepherd moons. How do the shepherd moons work? Well, in this diagram here, imagine this is the planet Saturn down here. And we have all the ring particles. So these are the rings right here. And we have these moons. Now, the thing is that the inner one always is going to be going faster. The outer one's going to be going slower, and the ring particles are going to be going in between speed. So that means that the shepherd moon that's inside is always going to end up going faster than the ring particles. So that means it always ends up ahead of the ring particles, pulling on the ring particles, pulling them faster. When they try to go faster, they speed up and they go out back into the ring. Likewise, what's going to happen is that the outermost moon is going to be lagging behind the ring particles. So the ring particles are going to be drifting out here, but they're always going to be getting in front of that moon. And so that moon's gravity pulls on it, slows them down, and they fall back into the ring. So the shepherd moons literally, by going inside and outside the ring, shepherd the ring particles back into the ring. Because we have these prominent shepherd moons right there, then that tends to kink that ring a little bit. Okay. Smaller shepherd moons probably would not kink or twist the ring as much. In fact, we believe that there's a lot more shepherd moons than we see. In fact, if they look right into the inky gap right here, if you look into the inky gap, there's this little bitty moon right there called Pan. And Pan's gravity is actually what's clearing out that inky gap. It's causing, particles on one side to drift back that way and particles on the other side to drift back the other way. And so it's helping clear that out. So we think a lot of these little ringlets that we see, a lot of the ringlets that we see in here might have little undetected moonlets in them. Okay, these spokes I said were oddities here that originate from dust particles in the rings being caught in the magnetic field. So these are like ionized dust particles, static electricity, and so they get caught in the magnetic field, and then they're moving around at a different rate than the rings are. So they're moving around with the magnetic field. They're probably floating just a a few meters above or below the rings. So they're not really very different from the rings, but they are moving along in the magnetic field. The other thing that we've noticed is that if you actually look at the density of the rings, there's like density waves that go through the rings. These density waves are due to gravitational distortions due to the moons. So why do we even have rings in the first place? Well, mathematician Edward Roche calculates that a rigid moon, if you get close to a planet, will fall apart. So we got a planet, and then we got a moon here. If the moon is held together by its own gravity, if it gets close to the planet, one part's trying to go faster than the other part, and you just shear it apart. Okay, and it just falls into little bits. Now, if it's held together by something other than its own gravity, that's different. For example, boulder is held together by atomic molecular forces between molecules and things. The space station is held together by bolts and rivets, that keep it together. It's not being held together by its own gravity. So things like that, even though they're inside the Earth's Roche limit, are held together because they are held together by something else. But our moon, Luna, if it gets close enough to Earth, would actually fall apart because it's being held together by gravity. So he works to get up an equation saying that the Roche limit, which is the closest you can get to a planet before a moon falls apart, depends on the size of the moon. The smaller the moon, the closer you can get to the planet before it falls apart. It also depends not just on the size of the moon, it's the mass of the moon. The more mass the moon has, then the farther away it can be. Okay, and it also depends on the mass of the planet. Okay, so actually there's a typo here. Little m should be mass of the moon, big M should be mass of the planet. But that would give you the Roche limit, and that would be how you would figure out how close you can get. And so one idea they have for the rings is that possibly one of these moons, an icy moon, because we're a long way from the solar system, so ice is a big constituent of how things build, something causes it to drift inwards. Remember, planets can migrate in and out. So likewise, we have a whole bunch of moons, so gravitational interactions could cause a moon to migrate in or out. So if this moon migrated inwards, it could actually fall apart and give rise to a ring. Okay, so if it migrates inside of its Roche limit, it would produce a ring. And so that's kind of what the Cassini data indicates, is that these rings are in fact relatively recent. Relatively recent in terms of the solar system. Solar system for almost 5 billion years old. The ring can be 1 billion years old and still be recent in terms of solar system. So our understanding of the rings is they're not necessarily a permanent feature, that they are something that is caused by a moon drifting too close and falling apart.